Hi, this is Yunhao Yang, and this video is for a crash course in A-star pathfinding. In this video, I'm going to talk about how to combine A-star pathfinding and Unity. And the basic idea behind A-star pathfinding is by utilizing a heuristic function. Similar to Dijkstra pathfinding algorithm, A-star pathfinding will also keep track on the shortest path and cost for each node, like for each what it says in the graph. The major differences is the A-star pathfinding will utilize a heuristic function, as I mentioned just now. The way using the heuristic function is it will keep tracking the it will keep it will also using a priority queue or heap to make sure the next node we're processing is all will be the node like the closest to the target. So basically, the heuristic function is used for calculating the distance between current node and the target node. And in A star, there will also be a all the heuristic score will be putting something like a will be used as a call it like a H score, and there will also be a G score in the algorithm. The G score is used to calculate the cost from the start node to the current node, and there is also a F score. F score is the sum of G score and NH score, and basically in the priority queue or heap, it will the the order of the nodes will be depends on the F score. So basically, every time I pop from a heap, it will always pop the one with the sum of the smallest sum of the distance from the start node to current node and the distance from the current node to the target node. And by using this system, just I mentioned just now, like you'll make sure like the node it pop will be considered as a really considered as the closest node to the target node. And because of this system, so in Dijkstra, the like for in Dijkstra, because there's no such system, I need to make sure I traverse the entire graph to make sure I get the shortest distance. And in A star, I don't need to because I can assume I'm always processing the closest node to the end node. So as long as I find the end node in the processing, I can make sure I already got the smallest path. This makes A star this gives A star a great advantage over Dijkstra. And here I will explain how I implement the entire algorithm. So first of all, I got a detection script. So basically, the use of this script is like I draw a straight line on each point, and each line will be like 60 angle to each other, and the line will be cross one point, which is the middle point. I can run an example here. So I'll just need to do a small modification here. Let me get rid of the entire stuff. In this example, I will run a detection on the original point, which is 0, 0, 0. And you can see there are three parameters here. The first one is the place I want to run detection. I want to detect if this point have any obstacles or like colliders in Unity. And the second one will be distance. The distance here I will set as 10. And the third one will be do I want to ignore any layer mask? And in default, I will do like I will ignore the second layer mask 2, which is ignore recast. Because if I don't do this, if I don't put in this parameter here, because ignore layer mask also run in detection, like which is also it will always have a ignore here. So which means like if I left ignore empty, it will not ignore any layer, which means that even if layer 2 call ignore recast, it will still be considered in the recast, because as long as I put in any ignore parameter, it will override the default ignore, which is like the second layer. So things should be alright. And if I start the oops, my bad. And I will showcase the detection here. So you can see when I run detection, it draws 3 lines here. And the reason I'm only drawing 3 lines is for saving runtime, because previously I have tried drawing 8 lines, which goes to 8 directions. That costs a very long time. So in the later I try to reduce to 3 lines. And basically these 3 lines can cover most of the area in this place. So that's why I'm doing it. So it can be much faster than drawing 8 lines in the actual game, and still not missing, only have a little reduction on the accuracy. And next part I'm going to talk about the pathfinding part. Before that, I'm going to add pathfinding back to the scene, and also remove this new code I wrote here. And in pathfinding, you can see first I will define a grid, because directly running detection on each point in the map is not really good idea, because that takes very long time, and especially this terrain is like 1,000 times 1,000. It means like if I run obstacle detection on pathfinding on each based on a scale of 1, it means I need to traverse like at the most 1,000 times 1,000, which is 1,000,000. I need to traverse at most 1,000,000. At most, like not at most, like because some point can be traversed multiple times. Like I need to traverse a lot of points to if there doesn't exist the shortest path. And because of this, I'm using grid. So basically, I've divided the map into with a scale. So right now the default grid will be 10. And also I wrote a public function to allow user to set any grid they want. And I will still use 10 here. So the default grid will be 10. So basically divide map into a block size of 10. So you will consider each block as a node. So this is how set grid works. So basically where is it? Oh, here. In set grid, it will calculate the cost map. So if I run the algorithm, you can see, oops, yeah. If I run the algorithm, you can see there's red dots for the entire map. There are red lines for the entire map, because I run a detection on each node of the map. So because I'm dividing grid into, I'm using grid of 10. So basically I'm divide the map into like from 1,000 times 1,000 to 100 times 100. That'll be saving a very long time in the actual pathfinding. And however, you can see this line is not really straightforward, because in this instance, in this instance of application, I only make sure every node I only make sure there are 8 directions, because in the actual game, in the actual like in the actual game, 8 direction usually works for the most of the time. There can be more directions. However, it can be like have a cost of longer runtime. So right now I'm using 8 directions, and you can see here I also have a high detection threshold. It means like when I run the detection, it's not on the height of 0, because in some stuff it may not be directly connect to the ground, and that's the main reason I'm having a high threshold here. Make sure I can also detect something in the middle of the air. So basically, this high threshold player can also set this high detection threshold. On you can set any height you want. Also, I can also allow player to set the ignore layer. And default, I'm still using layer 2, and default high detection threshold is also 2. And after set grid, so next main part is A-star pathfinding. In this method can take a start node and an end node, and what it does is like it will return a path from end to start, and basically you can see here. First of all, it will normalize these two positions, because this step just makes sure like it's normalized to the closest grid, like to the closest block, because the input vector 3 may not be an actual block. It may be like, so for example, right now I'm dividing into 10, so maybe the input will be 43 or 5, like 105, which is not a block. So it will be, the normalization will be change the input position to the nearest block. And the next step, I will have an initial node. So basically, I have a heuristic function here and an f function, an f score which is directly equal to the h score, because it is a start node, and so the cost from start to start node is 0. And I have a heuristic function here. So basically, this heuristic function, it will calculate the x difference and y difference. And the main reason I'm using this function here to get a heuristic score is like I'm abstracting like a right triangle and has two equal sides. And basically in this triangle, the two sides that have equal value will have a value of 10. And we know the third side of a right triangle we can get it by applying a square root by using a square root of the sum of the square of the two sides are next to the right angle. And in this case, those two sides have a length of 10, and the third side will have a length of like 14.14, something like that. And I directly take the integer part because I don't want to waste time on calculating the decimal part. So basically, this one will, though this function will not, though 14 will not have exactly the same value as 14.14 and exactly the same value of 14.14, but it's already pretty close. And this line will be like, for example, when I'm thinking about getting from this getting distance from this node to this node, it will calculate this. It will count blocks on this, and after there are 5 blocks here, and it will time this five blocks by 10, which get resulting in 50, and then it will count these 2 blocks here, and because these 2 blocks are going this row, which have a cost of 14, so you will count these 2 blocks as 14, like 14 times 2. This is how this heuristic function works. Because I'm only working in eight directions, so this heuristic function will work here. However, there's also a backup plan of heuristic function, which I put here. However, this one is a redundant function, so I probably will delete this in the future. So this one is basically the calculation of the third side of the right triangle. Instead, it's not applying a square root because I think square root will taking a lot of time. So I think applying square root might cause a really huge reduce on the runtime. Like, will have a huge impact on runtime efficiency. And however, this distance already can be used in comparison. So I'm not taking a square root here. In the next part, I'm having a map heap because I don't find a priority queue on my current C#, like in my current net version. So I have to make a priority queue or heap on myself, and this is a heap. Like, it's basically a normal heap. Instead, you're taking a node as input and a node as output, and what it does is it compares the F score in the node. So in the next step, I will initialize a node array, and because I will directly record every node information on in this array, because I'm I use a function to directly convert a vector 3 value into index. It can be shown. It is shown in here. So basically, I'm considering the x value and the z value of the vector 3 as an index for 2-dimensional array. And I'm using a function here to reduce the 2-dimensional index to 1-dimensional index. This is how it works. I also make a static function, so it makes the conversion much easier by using static function. There's also a static function by converting index to vector 3. However, it's not counting the y value which is hide in the game. So basically, this entire pathfinding is by converting a terrain into a 2D map. Because currently, this function can be modified to consider 3D. However, it will taking much longer time to do the pathfinding. And in the next part, I directly push the start node to the heap, and then I then go into a loop. So basically, in a loop, every loop, like, it will pop one item from the heap, and it will search the surrounding workable node of the current node, and then it will do a processing. Once it found, oh, by the way, the heuristic function here can also be used to calculate the distance. So that's why I directly use the heuristic function to calculate the distance between the current node and the neighbor node. So for each neighbor node, it will count. What it does is it will compare the current G score to the neighbor node's G score to the sum of the current G score and the distance. if it find the current G score will be smaller, it will update the node. So basically, it will make the current node as a previous node of the neighbor node. Also update the GHF scores, and then you push this node to the heap. Like it does not consider whether this node is in the heap. I can also add a bool array to make sure to detect if any node is in the heap. However, right now I'm thinking this is not quite necessary because it will increase the it will increase the memory usage. So what I'm doing is like I directly push it to the heap, because if there's no change on this score, so there will be no change on the neighbor score. Like if there's no change on this node score, there will be no change on the neighbor node score, and it will be the loop will be stopped when you find the target node, when you find the current node is the target node, or you find the heap is empty, which means there's no shortest path from the start node to the target node. After this stop, you start constructing a path. So basically, it will be start from the you will start from the end node and directly find a path to the start node. However, if there's no path, it will be like it will immediately stop at the end node, because the way to consider is that the last node in the path is it will see if the index of the current node is same as the prev index. If it is the same, it means like there's no nodes before the current node, so you will stop here. And after get the path, it will be returned by a star function to the game manager, which is here. And I simply put a cube on each vector 3 to represent the path, which you can see here. That's the overall explanation of the entire algorithm. And next step I will put some obstacles. Wait. Okay. Oh damn! Sorry, I should disable this. You can see the start node is somewhere around here, and the end node is somewhere around here. You can see it generates a path just bypass these two obstacles. I can try to change the position of these two obstacles, and you can see some different results. You can see this time going from this way. And let me try to adjust this one. You can see going from here. However, I'm not sure why it's going a little bit inside of the cylinder. That sometimes happens, but I'm not entirely sure what caused this. Oh wait. And I can try to make this one even larger. Wait. I want to make sure it's not large enough to cover the start node. Yep, this one's directly coming from here. So basically, this pathfinding did takes a really short time, and it does bypass the obstacle on the path to find the shortest path from start point to the end point. That's all. Thank you.